For decades, people have assumed that nuclear fusion has one defining challenge: building a reactor capable of sustaining the extreme conditions needed to produce energy. That assumption has shaped nearly every discussion about the future of fusion, but what if one of the industry's oldest obstacles was never inside the reactor at all? Imagine standing on the shoreline and looking across an ocean that already contains enough potential fusion fuel to power civilization for thousands of years. The remarkable part is that this has never been a secret. Scientists have long known that deuterium, a key fuel used in many fusion concepts, is naturally present throughout Earth's oceans. The real question has never been whether the fuel exists. It's whether extracting it can be done efficiently enough to make commercial fusion practical. For years, the energy required to separate deuterium from seawater made the entire process difficult to justify on an industrial scale. That single limitation quietly influenced reactor designs, fuel economics, and long-term investment strategies around the world. Now, emerging research suggests that this decades-old assumption may finally be changing. If these new approaches continue to prove themselves, the conversation around fusion could shift from finding fuel to simply accessing what has been in front of us all along. So the real question isn't whether the ocean contains enough fusion fuel. It's whether seawater could become the foundation of tomorrow's clean energy economy. One of the biggest misconceptions about nuclear fusion is that it faces a shortage of fuel. In reality, the opposite has always been true. Long before today's fusion startups attracted billions of dollars in investment, scientists understood that one of fusion's primary fuels, deuterium, exists naturally in enormous quantities throughout the world's oceans. Although the concentration is relatively low in each liter of seawater, the sheer size of Earth's oceans changes the equation entirely. When multiplied across the planet, the available supply becomes so vast that, for practical purposes, it can be considered nearly inexhaustible on a human timescale. In other words, nature has already provided an extraordinary fuel reserve. The challenge has always been turning that reserve into something economically usable. That distinction is important because abundance alone does not create a reliable energy source. Oil existed beneath the ground long before drilling technology made it valuable. Natural gas remained largely unused until transportation and infrastructure improved. The same principle applies to fusion fuel. Having access to an immense resource means very little if recovering it requires excessive amounts of energy, expensive facilities, or complicated industrial processes. For decades, this extraction challenge quietly shaped the economics of fusion research. Engineers had to assume that producing reactor-grade deuterium would require large-scale infrastructure, significant operating costs, and continuous energy input. Those assumptions influenced everything from reactor planning to national energy strategies. As a result, discussions about fusion often focused on plasma physics and reactor design, while overlooking a much simpler question. Could the fuel itself be obtained more efficiently? That overlooked question is now receiving renewed attention, and answering it may prove just as important as any breakthrough inside the reactor. For much of the modern history of fusion research, the conversation around fuel was shaped by a single assumption. Extracting deuterium from seawater would always be an expensive, energy-intensive industrial operation. Scientists were never worried about running out of fuel. Instead, they were concerned about the enormous effort required to separate a tiny fraction of deuterium from ordinary hydrogen on a scale large enough to support future fusion reactors. This challenge led governments and nuclear agencies to rely on technologies originally developed for heavy water production. Among the best known was the Girdler sulfide process, a chemical exchange system that became the standard method for producing heavy water for certain types of nuclear reactors. It represented an impressive engineering achievement for its time, but it also revealed just how difficult isotope separation could be. Unlike a simple filtration system, the process required large industrial facilities operating continuously under carefully controlled conditions. Massive networks of towers, heat exchangers, pumps, and chemical processing equipment worked together around the clock to gradually separate deuterium-bearing water molecules from ordinary water. Every stage demanded significant electricity, precise temperature control, and constant monitoring. The scale alone was remarkable. Some heavy water production plants covered hundreds of acres and consumed enough power to resemble small industrial cities rather than ordinary manufacturing facilities. Building one required billions of dollars in infrastructure, years of planning, specialized engineering expertise, and long-term government support. These were not facilities that could simply be constructed wherever a future fusion reactor happened to be located. More importantly, the economics of the process created an uncomfortable reality. Producing deuterium consumed so much energy that the overall efficiency of the future fusion fuel cycle became an important consideration. Engineers had to ask a fundamental question. If obtaining the fuel already required substantial energy and financial investment, how much net benefit would a commercial fusion reactor ultimately provide? When governments evaluated potential fusion programs, fuel production became part of the economic model. Reactor costs were only one piece of the equation. Analysts also considered transportation infrastructure, chemical processing facilities, storage systems, and long-term operating expenses associated with maintaining a stable supply of deuterium. These assumptions quietly shaped feasibility studies, investment decisions, and national energy roadmaps around the world. As a result, countries with existing nuclear infrastructure appeared to hold an advantage. Nations that already possessed heavy water production capabilities or advanced chemical industries were seen as better positioned to support future fusion technologies. For everyone else, establishing an independent fuel supply looked like an expensive and complicated undertaking. The limitation wasn't caused by a lack of scientific understanding. Researchers fully understood where deuterium was located and how it could be extracted. The obstacle was that the available methods relied on chemistry that offered only gradual improvements after decades of optimization. Every efficiency gain became increasingly difficult to achieve because the molecules being separated behave almost identically. Extracting one isotope from another demanded considerable energy, simply to exploit a very small physical difference. Over time, this became accepted as a permanent reality rather than a temporary engineering challenge. Fusion researchers concentrated on solving plasma confinement, superconducting magnets, advanced materials, and reactor stability because those appeared to be the largest remaining hurdles. Fuel extraction was viewed as a mature technology. Costly, yes, but largely solved within its existing limitations. History, however, has repeatedly shown that industries can change when someone questions an assumption everyone else has accepted. Air travel became affordable, not because physics changed, but because engineering and manufacturing evolved. Solar energy transformed after production costs collapsed rather than after new sunlight was discovered. In many cases, the biggest breakthroughs occur not by improving an existing system a few percentage points, but by approaching the problem from an entirely different direction. That possibility is now beginning to emerge in the field of deuterium extraction. Instead of trying to make traditional chemical separation slightly more efficient, researchers are exploring methods that bypass many of its limitations altogether, and that shift starts with a technology that relies less on large chemical plants and more on the precision of light itself. For decades, improving deuterium extraction meant refining the same basic chemical processes. Engineers searched for better catalysts, more efficient heat management, and incremental reductions in energy consumption. Progress certainly happened, but it was measured in small percentages rather than transformational leaps. The underlying assumption never changed. Separating hydrogen isotopes would always require processing enormous volumes of water through energy-intensive industrial systems. A new generation of researchers began asking a different question. Instead of improving the chemistry, what if they changed the physics? That question opened the door to laser isotope separation, an approach that replaces broad chemical processing with highly selective molecular targeting. Rather than treating every water molecule the same, the goal is to identify only those containing deuterium and interact exclusively with them. At first glance, the difference may sound subtle. In practice, it represents an entirely different philosophy. Traditional chemical methods process every molecule that passes through the system, even though only a tiny fraction actually contains the isotope engineers are trying to recover. It's comparable to searching an entire warehouse by opening every single box one at a time. Most of the work produces no useful result because nearly everything being handled isn't the desired material. Laser-based separation attempts something much more precise. Every molecule naturally absorbs light at specific wavelengths depending on its atomic structure. Although ordinary water and deuterium-containing water behave almost identically in chemical reactions, they respond slightly differently when exposed to carefully tuned frequencies of infrared light. Those tiny differences create an opportunity. By adjusting a laser to an extremely precise wavelength, researchers can excite primarily the molecules that contain deuterium while leaving the overwhelming majority of ordinary water almost completely unaffected. Instead of forcing billions of unnecessary molecular interactions, the system concentrates its energy on the molecules that actually matter. From an engineering perspective, that's a profound shift. Think about modern manufacturing. A factory using a precision robotic arm consumes less effort than one relying on manual inspection of every component. In medicine, targeted drug delivery seeks to affect diseased cells while minimizing impact on healthy tissue. Modern logistics use artificial intelligence to optimize shipping routes instead of moving every package through identical paths. Laser isotope separation follows the same principle. Rather than increasing the size of the process, it increases the accuracy of the process. This selective approach has several theoretical advantages. Because less energy is wasted interacting with ordinary water molecules, the total energy required for isotope separation has the potential to decline significantly. Smaller processing systems become more realistic. Operating costs could eventually decrease, and modular designs become easier to imagine than massive centralized chemical plants. Of course, promising physics does not automatically create a commercial technology. The nuclear industry has seen many laboratory breakthroughs that never survived the transition into large-scale industrial production. A process that works perfectly under controlled conditions may encounter entirely different challenges when operating continuously for months or years. Throughput, reliability, maintenance, equipment durability, and manufacturing costs all determine whether an innovation can move beyond scientific journals and into the real world. That skepticism is exactly why researchers have spent years moving beyond theoretical models toward pilot-scale demonstrations. Instead of asking whether laser separation is scientifically possible, they began testing whether it could outperform conventional methods under realistic operating conditions. Those experiments attracted growing international attention because they focused on the one question that matters most to industry, not whether the technology works, but whether it works better. And according to recently published research, that question may finally have an answer worth paying attention to. Scientific breakthroughs rarely change an industry overnight. Most begin as carefully controlled laboratory experiments, followed by years of testing, peer review, and gradual improvements before anyone considers commercial deployment. Nuclear technology is no exception. Because of the enormous safety, engineering, and financial requirements involved, researchers are typically cautious about making bold claims until results can be reproduced and independently verified. That is why recent developments in deuterium extraction have attracted attention well beyond the fusion research community. Instead of simply proposing a new theory, several research teams have moved into pilot-scale testing, where technologies operate continuously under conditions that more closely resemble real industrial environments. This stage is significant because it bridges the gap between scientific possibility and practical engineering. A concept that performs well in a laboratory must still demonstrate stability, efficiency, and consistency before it can be considered for large-scale adoption. One of the most closely watched areas has been the effort to reduce the energy required to separate deuterium from seawater. Traditional extraction methods have long been criticized for consuming substantial amounts of energy, limiting their economic attractiveness, even though the raw material itself is virtually unlimited. The latest pilot studies suggest that newer laser-assisted approaches may be capable of lowering that energy requirement. While the reported improvements vary depending on system design and operating conditions, the broader implication is what matters most. For the first time, researchers are discussing extraction systems that could potentially outperform conventional industrial methods rather than merely matching them. Engineering history is filled with technologies that remained largely ignored until they crossed a critical performance threshold. Early electric vehicles existed decades before they became commercially competitive. Solar panels generated electricity long before they became one of the world's fastest-growing energy sources. High-speed internet relied on technologies that spent years inside research laboratories before transforming global communication. In many cases, industries don't change because something becomes possible. They change because something becomes economically practical. If extracting deuterium requires significantly less energy than previous methods, the economics of future fusion projects begin to look different. Lower operating costs could reduce the long-term expense of fuel production. Smaller, modular extraction systems may become feasible where enormous industrial facilities were once required. Countries without legacy heavy water infrastructure might eventually gain new options for supporting fusion research and future power generation. However, it is equally important to understand what these results do not mean. Pilot-scale success does not guarantee commercial success. Research systems operate under carefully managed conditions, with specialized equipment and dedicated engineering teams. Scaling those systems to produce fuel continuously for years introduces challenges involving maintenance, manufacturing costs, environmental conditions, and operational reliability that cannot be fully answered by pilot projects alone. That is why most experts continue to describe these developments as promising rather than definitive. The data deserves attention, but it also requires careful validation through additional testing, independent replication, and long-term operational experience. Still, even cautious optimism represents a meaningful shift from the way fusion fuel extraction has traditionally been viewed. For decades, the industry largely accepted that deuterium production would remain a fixed cost built around large chemical facilities. Today's research suggests that assumption may no longer be permanent. If future studies continue to confirm these early findings, fuel extraction could evolve from one of fusion's most persistent economic constraints into a far more manageable engineering challenge. And achieving that transformation depends on something even more interesting than lasers alone. The real breakthrough may come from combining several technologies, each solving a different part of the problem, into a single integrated system. One of the biggest misconceptions surrounding this research is that a single invention suddenly solved deuterium extraction. In reality, breakthroughs of this scale almost never happen because of one technology alone. They happen when several independent innovations mature at the same time and begin solving different pieces of the same engineering puzzle. Instead of relying on one revolutionary machine, the latest system designs combine multiple technologies into a coordinated process. Each stage performs a specific task, allowing the next stage to operate more efficiently than it could on its own. Rather than replacing every existing technology, the approach improves the entire workflow from seawater intake to fuel production. Although seawater contains the deuterium researchers want to recover, it also contains dissolved salts, microscopic organisms, suspended particles, minerals, and countless other impurities. Feeding untreated seawater directly into a precision extraction system would quickly reduce efficiency and increase maintenance requirements. For that reason, the first step focuses on cleaning the incoming water. Advanced filtration systems remove larger particles and biological material before the water enters the next stage. This isn't unique to fusion research. Modern desalination facilities use similar methods to protect sensitive equipment from contamination and long-term wear. By removing unwanted material early, the entire extraction process becomes more reliable. At first, this may seem unrelated to deuterium production, but it plays a surprisingly important role. Dissolved salts and minerals can interfere with later processing stages, particularly those requiring high levels of molecular precision. Reverse osmosis or similar desalination techniques create a much cleaner water stream, allowing downstream systems to operate under more controlled conditions. The partially purified water flows into a membrane-based concentration system. Rather than attempting to isolate deuterium immediately, these specialized membranes gradually increase the concentration of deuterium-containing water molecules. The improvement at each stage is relatively modest, but the effect becomes much more significant when multiple membrane layers are arranged in sequence. This principle is common throughout industrial engineering. Oil refineries separate crude oil through multiple stages instead of a single operation. Water treatment plants purify drinking water step by step rather than relying on one giant filter. Semiconductor manufacturing depends on dozens of highly specialized processes, each preparing the material for the next. The membrane cascade follows the same philosophy. Instead of demanding that one machine accomplish everything, each stage performs a small improvement that collectively produces a much stronger result. Once the concentration reaches a higher level, the laser system becomes dramatically more effective. Earlier generations of laser separation struggled because too few deuterium-containing molecules passed through the beam at any given moment. Processing vast quantities of ordinary water wasted valuable laser capacity and limited overall throughput. By increasing the concentration beforehand, the membranes effectively deliver a richer stream of target molecules to the laser stage. Even highly sophisticated equipment cannot maintain peak performance indefinitely without adjustments. Ocean temperatures fluctuate throughout the year. Water chemistry changes from one coastal region to another. Seasonal variations influence operating conditions in ways that fixed industrial systems cannot easily predict. Modern control systems continuously monitor dozens of operating variables, including temperature, pressure, water flow, and equipment performance. Rather than requiring technicians to manually recalibrate the system whenever conditions change, intelligent software can make small adjustments in real time to help maintain consistent operating efficiency. Pilots determine the destination, but sophisticated onboard computers constantly adjust flight controls to compensate for wind, altitude, and weather conditions. The aircraft remains on course because the system is continuously adapting to changing circumstances. Instead of assuming the ocean will always behave the same way, automated control systems allow the extraction process to respond dynamically as environmental conditions evolve. That adaptability becomes increasingly valuable when equipment is expected to operate continuously over long periods. Interestingly, one additional benefit emerges from this integrated design. Because desalination is already part of the treatment process, the facility naturally produces fresh water alongside deuterium extraction. While clean water is not the primary objective, it represents a useful secondary output that could provide additional value for coastal regions where freshwater resources are limited. Combining energy infrastructure with water production could improve the overall economics of future installations by allowing one facility to support multiple public needs. Taken individually, none of these technologies completely transforms fusion fuel production. But when each component is carefully integrated into a unified system, the overall process becomes far more capable than any individual technology could achieve by itself. Of course, integrating several advanced technologies also introduces new engineering challenges. More components mean more maintenance requirements, additional operating costs, and new questions about long-term reliability. Before these systems can support commercial fusion reactors, they must prove they can operate efficiently, not just for weeks or months, but for years. And that is where the next phase of development becomes critical.